Hello everyone, we are Team Tensor, and we are collaborating with Pacific Northwest National Laboratories. Our team members consist of myself, Adam Nassar, Marcel Makundi, Blake Coulter, Derek Guscott, and Nathan Balcarcel. As we've discussed in previous semesters, RMAX is a prototypical C++14 interface over MPI3 RMA, which focuses on providing a thin layer above MPI RMA and at the same time aims to improve the programmability of MPI RMA. In this sprint, we focused on four major things: researching and implementation of C++20 features. We implemented higher dimensional testing, gap checking between multiple processes, and continued development on our debug branch.
Hi everyone, my name is Derek and I'm going to walk you through two new test cases we have implemented for our app demo section of this video. The first test case I'm going to show you demonstrates our ability to run RMAX with windows of higher dimensions, in this case 9 dimensions. The first thing we do in this test case is define two vectors called dims and pgrid. These vectors are going to represent the start and end coordinates of each process. We'll then create a global view window with two processes and we'll feed the coordinate vectors we created in the last step. After the window is created, we're going to fill the entire window with 1s. Then we fill a vector of size 512 with 3s, and we attempt to put all the values in this vector into the center hypercube, which overlaps both processes. Lastly, we check that the area we have attempted to fill with 3s has indeed filled with 3s. If so, we mark the test as passing. So right now I'm just going to run the test for you guys so you can see that it works real quick. And as you can see, the terminal outputs pass, which means our test is successfully passing. The second test case I'll be showing demonstrates our new gap check feature. With the new code we have added to RMAX, we are able to detect if there is a gap between processes. Essentially, this new code checks every part of the window we create and makes sure that our processes fill up the entire window area. If there is a gap between processes, the window throws an error. Much like the last test case, we define coordinates for 5 different processes. For this test case, we want there to be a gap so our new code can detect it. As you can see, we've commented out the last process, as including it would fill in the gap and cause our test not to pass. Next, we create the window with 4 processes and feed it the coordinates. During this step, if a gap is detected, the window constructor will throw an exception, and this flag, exception was thrown, will flip to true. At the end of the test, we check the value of exception was thrown, and if a gap was detected, that is, exception was thrown equals true, we mark the test as passed. Notice that when I run this test, I need to define the macro debug check gaps, as not including this would cause the gap check not to run. As you can see, no assert errors appear in the terminal, meaning that exception was thrown is indeed true. This means our code successfully detected a gap and the test has passed.
Hello, my name is Nathan, and I was working with the higher dimensional test during this sprint. So, we need higher dimensional tests to make sure complex cases work correctly. RMAX is complex, and we need to make sure it remains stable and consistent, even when working with a high workload. We also want to make sure RMAX actually supports these test cases, since any errors, when we go to 9 dimensions or higher, mean we have to revise the code. We'd like to check edge cases as well, to ensure that any number of dimensions will work functionally the same no matter what. And we want to make sure RMAX is scalable, so no matter what shape or size of window we use, it should continue to function as expected. Roadblocks. So when working with higher dimensional tests, we realized a lot of problems. Most importantly, higher dimensions are very difficult to visualize, especially when you have to write down exact coordinates for each process. As you can see, we have a few diagrams here laid out trying to grasp the concept of higher dimensions. There are some steps we took to simplify multiple dimensions. We realized that we can think of 4+ dimensions as simply a 3-dimensional figure and ignore all of the rest of the coordinates. This worked for some test cases, but we wanted to make sure we were testing RMAX to its full capability, so we needed to adapt. One way we did this is by finding an algorithm that works for both 3 dimensions and higher. So once we realized how coordinates actually worked, for example, cutting away a piece of a cube. We looked at what that did to the coordinates and noted down any patterns. We realized that we can use these same patterns no matter how many dimensions we had. So although we couldn't quite visualize the figures we were making, we were able to make them into a test case and actually test them correctly. Another roadblock is we realized Armax is very inconsistent. Initially, we thought it used both inclusive and exclusive coordinates. However, we realized that all coordinates are actually inclusive. The problem was there are start and end coordinates, and sometimes there are starts and size coordinates. And when you have both of these mixed together, it can get a little bit confusing since the same set of coordinates will look different in different areas of the code. Additionally, we had a little bit of trouble making the test complex and robust, especially with a 9-dimensional test case that we made. We realized, as I mentioned earlier, we can actually create an algorithm to create 9-dimensional figures and fill in all of the gaps and spaces and have it actually be a complex figure that isn't just, partitioning the area into 4 pieces. We could actually break it down into various different shapes, and we decided that that would be the best way to write a test case for Armax. There's also a little bit of trouble in actually testing to make sure all the test cases were running successfully. Each test case works a little bit different and success is defined in a different way. Sometimes you want a certain area to be filled in with a certain value. Sometimes you want the test to crash. So it took a little bit of time to figure out how to actually test all of the test cases to make sure they were all passing. Another thing we did during the sprint is implement gap checking. So in Armax, all of the processes should fill in the entire window. There should be no gaps between the processes. However, Armax did not have a way to test for this, so we had to implement this ourselves. So we came up with a few different ideas for actually checking gaps, including looking at exact coordinates and figuring out what tiles have been included and which haven't, but that wasn't very scalable and it was very memory intensive. So there was a bit of problems coming up with an algorithm, but eventually we found one that could scale up to infinite dimensions. Another problem with gap checking was actually retrieving data between processes. So when we actually create a window, each process has its own set of coordinates, and these coordinates are unique to its process. So these sets of coordinates aren't actually globally available. We have to collect them ourselves. So there was a bit of trouble in figuring out how to share this data between different processes, but eventually we were able to figure it out and we could feed this data into the gap checking function. Alright, that's all I have. I'm gonna pass this over to Blake. I'm gonna head out.
Hello everyone, my name's Blake, and today I'll be discussing how C++ features fit into Armax. What we wanted to get our features was to clean up code for readability, decrease time for maintenance, and take advantage of asynchronous features. In the past, we showed how features will speed up the runtime of our code, and now I think is a perfect time to discuss how features will clean up the code for readability and decrease time of maintenance. The paramount example being right at the heart of Armax, this chunk of code is in our function for evaluating expressions and building our expression trees. And it really just shows how bad the old handle system was, with this 20 lines of code being neatly reduced down into 2 lines of code thanks to features. Now I'll pass the torch off to Marcel for the retrospective.
Hi, my name is Marcel, and I'm going to be talking about the retrospective for this sprint. In terms of what went well, we had really good communication this sprint while we were working together at kind of doing the meetings. And speaking of the meetings were more frequent and longer this sprint, which helped us get a lot more work done than last time because we're not cutting up the work among several different meetings. So there's not like the cold start at the beginning of a meeting. Working into groups, as it has been in the previous sprints, has been really good for productivity, allowing us to parallelize our work across different features. And by working together in pair programming, we were able to work a little bit more fairly by spreading the cognitive and time load among multiple team members, but also we were able to get through roadblocks and mistakes a lot faster this time, which sped up development quite a bit. We also didn't meet as frequently with our sponsor because a lot of the features we've been working on are multi-sprint commitments. And so there's less and less to update the sponsor on a weekly basis. So we've kind of just been meeting ad hoc, and that's been working a lot better for us this sprint. Some things we'd like to improve is making our meetings a little bit more consistent time-wise. And I think this would just help kind of in terms of allowing us to plan ahead for these kinds of things, and also so that no one's getting left behind throughout all the meetings. And by making our commits smaller and more frequent, we hope to actually be able to track our progress throughout the sprints a lot better. And that goes along with the Kanban board use, because we'll use that to track that progress. For changes we plan to implement next sprint, the first is to have a standing meeting date. So even if we don't meet every week or every day or whatever the meeting date ends up being, it'll be really useful to have a time where we know that everyone's available so that we can meet if we have an urgent question or some sort of confusion that we can all resolve together. Also, for assigning and working on individual issues, we hope that this will lead to the smaller commits that we talked about earlier, and it'll also make our progress a little bit more consistent and trackable, hopefully. And speaking of trackable progress, we want to track all of our issues in the repository. And more importantly, we want to track kind of smaller issues rather than the larger overarching issues we've been tracking thus far. And that way we can kind of break up the problems into smaller parts and work on them again in parallel, which will be better for our productivity.